Okay, welcome back. Well, we've seen before, just a reminder, I caught the convolution layer, which gives us, and then a nonlinear layer or nonlinearities, the ReLU and so on. And I mentioned some of the drawbacks in the last video about ReLU, meaning namely the dead neurons. But then I forgot to mention that there are variants of the ReLU, like the noisy ReLU or the leaky ReLU or so, other ones, which cover the shortcomings of the ReLU, the normal ReLU. Now, once you have your output from the activation function, we're going to now see the pooling layer. So what does pooling do is it replaces the output of the network from these nonlinearities here at a certain location with a summary statistic of the nearby outputs, meaning that you have a certain region and then you replace it with a statistic or with another operation. For example, in the case of the max pooling, which is popular, you take a neighborhood, a region of the output from this layer, and you take the maximum of that. That's why it's called maximum pooling. Alternatively, you can take the average, and that would be called the average pooling. So you report the average output, or you can take the L2 norm. And then when you replace this neighborhood with the maximum, for example, you're reducing the size of the output here. So in a way, when you're feeding this to the subsequent layer, you're reducing the computation for these upper layers. And then because also you're replacing a neighborhood with, for example, the maximum, in the case of max pooling, then this is some sort of a nonlinear downsampling operation that you're performing. And the pooling layer provides translation invariant, as we're going to see in the next slide or explain in the next slide. And this is important because when you have features here, and if your pooling is translation invariant, so if you have certain features, for example, you're trying to detect a face in the image, and then your features are the eyes, the nose, and the mouth, then the pooling layer doesn't care where these eyes and nose and mouth are. It is just as soon as it detects these features, it will recognize that this is a face. So this translation invariance property is important, okay? And then to explain this translation property, so let's say this is the output after your activation layer. So you have 0.11, 0.2, and 0.1, and you do the max pooling over a certain neighborhood. So it's a 3 neighborhoods. So for example, for these 3, you replace these 3 by just one value, which is the maximum in the case of the max pooling. So the max of 0.11 and 0.2 is 1. So it'd be 1. Now you take these 3, you replace these 3 with the maximum of these 3 values, and the output will be 1. Here, the maximum of these is 0.2. Here, the maximum of these 3 is 1. So this is the max pooling operation. We're going to see it in the case of images. Now, in the case where you have translation, so this would move here. So for example, you have 0.3 here. This would move here, this would move here, and so on. And then when you do the max pooling in this case, you can see that you have 1 here. You take these 3. The max of these 3 is 1. You take these three, the max is 1. You take these three, the max is 1, and so on. And this max of these three is 0.3. And you can see that the features have moved. None of the nodes has the same value. As you can see, 0.1 is 0.3, 1 is 0.1, and so on. So the features have moved, but then the output of the max pooling layer has, so every value in the bottom has changed, but only half the values in the top have changed. So you're still able to detect these features, okay? So it's invariant to the translation. The max pooling is invariant to translation. So again, max pooling, the maximum activation is chosen from the selected block values. Let's say this is the output of after you apply your ReLU. So you take a block of values. So for example, a pooling filter of dimension 3 by 3. And then similar to the convolution, and then you replace it with the maximum value in this block. So the maximum of these three, of all these 9 values is 8. So you put here 8. And similar to the convolution layer, we need to specify the size of the pooled region and the stride. So in this case, the size of our filter is a 3 by 3, and the stride, we're going to move it either by 1 step or 2 steps. So we define the step that, or the stride that we want to apply. And these are hyperparameters of the max pooling layer. If the size of the pooled region is given by f, for example, in this case, we have a 3 by 3, so f is a 3 by 3 with a stride s. For example, here it's a stride s equal to 1, as we're going to illustrate. The size of the output feature map can be given by this formula. So here H is a 5 by 5. So this feature map is a 5 by 5. So our H is 5. And then our F is 3. So 5 minus 3, 2 plus 1, which is the stride. So we're going to have a 3 by 3. Same thing for the width, same formula. So we're going to have a 3 by 3. And as again, if we have a stride s equal 1, we move, we take the maximum, we move, we take the maximum, and so on. So you can see here that the maximum value is 5, so we put 5 here. Maximum value is 6, we put 6. Maximum value is 5, we put 5. And the maximum value in this block is 5, we put 5. So common setting, usually we take the size of the pooling layer, pooling filter to be 2 by 2. So F equal to 2. We usually take a stride S equal to 2. And this, if we do this, F equal to 2 and S equal to 2, this discards exactly 75% of the activations in an input volume. So you're just retaining 25%. Another slightly less common setting is to use 3 by 3 receptive fields or a filter or a pooling filter of size 3 by 3 with a stride of 2. It is very uncommon to see receptive field sizes for max pooling that are larger than 3 because that would be too lossy and aggressive. I won't give you a good performance. Now, an observation. So we said that the pooling layer has hyperparameters like the size of the pooling filter and the stride. But then when you do backpropagation, the backpropagation does not affect the pooling layer. Okay, thank you.